Okay, good morning. Okay, so let's get started. All right. So last week's lecture and this week's lecture are both very important. All right, because they give you the framework that you need. Okay, to put the entire architecture in place. All right, and together with whatever device drivers you have already developed in the first half, you can sort of finalize the whole plan for the project. All right. So I've already uploaded the labs all the way to lab 9. All right. So you don't need to wait for the lab. Right? Once we finish the class, you can go and try and understand how all these different architecture work. All right, and then you can decide which one you want to use. All right, for the project. Okay. So we will first do a quick recap of the RTOS and the RTX principles. Okay, and link back with one of the mutex related concepts, all right, which we talked about, and then we'll go on to the inter-process communication. Okay, so let's just so now we have learned quite a bit of the OS. All right, we have learned how to create multi-threaded code. All right, how context switching works. Okay, and now that we switch to OS, how the design of the code also changes. All right, and we have talked about protecting shared resources and also synchronizing using semaphores. All right, so let's come back. All right, and why do we want to use RTOS in the first place? All right, so again, one of the key things is we want to be able to have some predictability and determinism. All right, and that relates to how fast you can respond to things. Okay, so responsiveness and speed. Okay, now fail safety is something that we will talk about later on. All right, and of course the scheduling and memory allocation. All right, so when we talk about a real-time system in general, all right, we say we want to meet timing constraint. All right, but at the same time, these timing deadlines can be defined as what we call either hard or soft. Okay, so what is a hard deadline? What is a soft deadline? Okay, a hard deadline means if I say that when the button is pressed, this motor must move within 200 milliseconds. It must activate within 200 milliseconds. If not, it is considered a critical system failure. Okay, very important for the system to be sustainable for me to fulfill this deadline. All right, so for example, okay, if you think about it, let's say when you're driving the car, all right, and you jam brake, okay, the ABS system must kick in, and you say that it must activate within 100 milliseconds of detecting that it's an emergency brake. Okay, so nothing else is more important than making sure that this event happens. If not, it's a life or death situation for the driver, all right, and the passengers in the car. All right, so that is a hard real time. Okay, so what is a soft real time? A soft real time means you need to update or you need to perform some action, but if occasionally you miss it once a while, it is not so critical. Okay, so for example, your real-time clock update, for example. Okay, so you have a system that keeps updating the timer every 1 second. It shows the time that is passed. So you may have a requirement to say every 1 second I update the timer to show that 1 second has elapsed. But occasionally, if I miss by a few milliseconds, instead of updating 1 second later, I update 1 second and 20 milliseconds later, or 1 second and 100 milliseconds later. Okay, once a while this happens, it can still be acceptable. Okay, it is not a system level failure. All right, so deadline can be really very critical or could be adjustable depending on the system you're designing. All right, and what we basically saw is the idea of a huge loop. All right, and then you sequence all your tasks, task 1, task 2, task 3, and so on. Okay, it's possible, and then you can have ISR to handle some of these urgent activities, but using RTOS now it is a lot more easier. So it's a lot more easier because you no longer need to think of the sequential flow. You think of very specific containers for each particular task. Correct? So you have one task for motor control, one task for Wi-Fi, okay, one task for LED, one task for audio. So when you design the task, you design it to perform some action, alright, which is your link to your low-level device driver, and then subsequently you think of how the tasks will talk to each other, how will they communicate, how will they synchronize. Alright, and it's very important because if you think about it, okay, if suddenly, okay, next week I come up and say I'm going to give you a new camera module, which I actually have, which I'm actually testing, okay, and I say you're going to integrate the camera module inside the project. It is much more easier with the OS, correct? Because now you can say that, okay, fine, I will create a new task to handle the camera module, capture the image, and then do the processing, and then I will figure out how to deal with the image classification or something like that. Okay, so it is actually a lot more easier, alright, to think about scalability, because you no longer think of where I slot it in. You just think of it, okay, now I create a new module. And then since I already have my OS architecture, I just think about how they will link up together. Alright, so OS, like I said, is a very powerful tool, okay, that allows you that flexibility to scale your project bigger or smaller. Alright, and as long as the architecture is done correctly, you find that it's very easy to do that. Okay, so again, just to link back to one of the first discussions we had, this GPS pothole system. Okay, so we saw that this idea of doing things sequentially, alright, is very, very troublesome, alright, and it's not very responsive. But now, if I think about designing the same system with OS, it's a lot easier now, correct? Because now I can say that I have one task for decode, for checking, for recording the switch and LCD, and each of these tasks will have a specific purpose, and then I decide how they talk to each other. Alright, so the whole framework will change once the OS comes in. Alright, so instead of doing what we did before, okay, now we use the OS, okay, and then we can go ahead. Okay, so the OS that you are currently using in this module is the RTX OS. Okay, generally all RTOS have similar behavior, similar APIs that we are using. Only the terminology will change. Okay, so some will say mutex lock, mutex unlock. Some will say mutex acquire, mutex release. Alright, so the terminology will change, but the concept behind it is the same. Alright, and this RTX is compatible with a lot of the ARM cores, alright, and the software tools as well. Alright, now if you remember when you first got your board, okay, and you first plug it in, it actually shows up as a USB drive, correct? And the very first time you unbox your board and you plug it in, it actually shows up as a USB drive. And then we made some changes to make it compatible with the Kill IDE. Okay. Now, if you revert back to the original version, all right, that is actually compatible with another OS called Embed OS. Okay. So after the module is over, you know, with the board, okay, if you have your own board, you can go and explore Embed OS. It is fully online-based development tool. All right, and they have their own variation of the OS, okay, which is compatible with the board that you have and a lot of other boards as well. Okay, so the board that you have is quite good. All right, you can use RTX on it, you can use Embed OS on it, and so on. Okay, so these are things you can explore. All right, and the real-time library, all right, of the Kill IDE actually provides a lot of underlying features. But when we build the project, we never include all of those libraries. Okay, we only include the basic ones. Okay, so the main thing that we want is actually the RTX kernel. Okay, and everything else we learn from the RTX kernel. Okay, the mutex, the semaphore, and so on. All right, but if you want to extend your project in the future, okay, you want to include networking, you want to include a file system on board, they have everything. So when you build the project, you can include all those libraries, and you have everything as part of your project. All right, and if you explore, the code is also open source. So if you really want to go and figure out how a mutex works, okay, how a semaphore works, you can actually go in and see the code. Okay, so the full source code is provided inside your project. Okay, so you can also go and explore, okay, when you're free to understand how all this is implemented. Okay, so the task creation and deletion, context switching, I think you've covered already. I'll not go through again. Okay, now I want to come to this. Okay, this prioritized scheduling. Okay, so we know that the whole idea of a real-time kernel is to make sure that whichever task is more important will always transition from ready to run, okay, and preempt a lower priority task. Okay, now what is the issue that this can potentially cause is this thing called a priority inversion. Okay, so what is a priority inversion? Okay, so let me draw for you here. So let's assume that I got two tasks, a high priority task and a low priority task. Okay, so I have two tasks, and this is the timeline. Okay, and both of these tasks share a resource called resource 1. Okay, so let's say this is the situation. You have high priority task, low priority task, and they both share a common resource, resource 1. And let's assume that initially the high priority task is already in a block state because of something else. It's waiting for some other resource, but it's in a block state. Okay, and if my low priority task runs, okay, a low priority task is running, and this is initially in a block state. Okay, so this is before time t equals to 0. That means before this, something else already happened, and my high priority task is blocked. So my low priority task runs, and it acquires resource 1. Okay, it acquires the resource first, alright, and after that, okay, at some point of time, the high priority task becomes unblocked, okay, and it transitions to the ready state. So because it transitions to the ready state, the scheduler responsibility is to always make the higher priority task run, correct? Okay, so I will transition, so this low priority task will now go to a ready state because it's been preempted, correct? And the high priority task will now transition to the run state. Okay, so let's say this is what is happening. And while the high priority task is running, it tries to acquire resource 1. Then what happened? It cannot acquire resource 1, correct? Because the low priority task already acquired it earlier. Okay, which means that now this task has to go to a block state. Okay, and if let's say there are no other tasks in the system, then your low priority task will now transition back to run, correct? And this will continue, okay? This will continue until a point of time where I release R1. Okay, so at this point of time, I release R1. Alright? So when I release R1, then what happened? Then the high priority task which was blocked will acquire R1. Okay, will acquire the R1 that it was waiting for, and then go to ready and then run. Okay, so this will now go to a ready state after that. Okay, because the high priority task has been unblocked. Okay, so what is happening here? So this duration from here to here is what we call the priority inversion. Correct? Why is it priority inversion? Because a high priority task is waiting for a low priority task. Alright? Okay, which is not intuitive because the whole idea of the RTX kernel and a real-time OS is to make sure that a high priority task always runs first. Okay, but in this situation, it is inverted. A high priority task ends up waiting for a low priority task to run and release the resource, okay, and then only I can continue running. Okay, so this is a potential issue. Okay, a potential issue in this kind of situation where a resource is shared between a high priority task and low priority task. Okay, but this is only one possible scenario, and it can get a lot worse. Okay, how can it get a lot worse? Okay, if there is another medium priority task, or a few medium priority tasks, medium priority 2, medium priority 3, and so on. And if, let's say, all of these tasks, okay, at this point of time, before the low priority task can release, okay, let's just say at this point of time, medium priority task becomes ready. Then what happens? I have to preempt the low priority task, correct? So medium priority task will run. So from here onwards, this task is ready. Then medium priority task runs. Then medium priority 2 becomes ready after that. Then this fella runs. Then medium priority 3 becomes ready after that. This fella runs. Correct? So all the tasks that are in between this high and low can preempt the low priority task before the resource is released. Correct? So end up what? Your high priority task keep waiting and waiting and waiting forever. Until at some point of time when all these tasks finish, then the low priority task can run, and then I say release the R1. Then only eventually my high priority task can run. Okay, so that is why this whole thing, okay, is what we call unbounded priority inversion. Okay, why we say unbounded? Because you cannot predict how long this thing is going to last. Okay, because there could be many tasks at all the different priority levels between the low and the high. Okay, and if this situation happens, then your high priority task can end up being in a situation where it waits for very long before the low priority task can actually run and release the resource. Okay, so this is an issue, okay, a genuine issue, okay, that we can face, okay, when you have shared resources between the high and low tasks. Alright, so how can we resolve this? How can we resolve this? Alright, so to resolve this issue, okay, so this is the explanation, okay, that I just did. Okay, the OS itself actually has a mechanism in place, okay, to help us resolve this issue automatically. Okay, and that is what we call priority inheritance. Okay, so with priority inheritance, what happens? The moment a high priority task is blocked because of a low priority task, the low priority task priority is elevated to match that of the high priority. Okay, so what does that mean? Okay, let's come back here. So if this same situation here, okay, this is the point where the block happens, correct? This is the point where the block happens. That means the high priority task is blocked waiting for the task, waiting for the resource. So at this point of time, what the OS will do is it will temporarily make the low priority task move up to be the same priority level as the high priority task. Okay, so it will temporarily inherit a higher priority. Okay, and why does this help? Because now I will not be affected by the medium priority task, correct? Okay, so none of the medium priority tasks can preempt me now because now I am at the same level as the high priority task. Okay, so you still have priority inversion. You never solve the priority inversion fully, but it's not unbounded. It is bounded by the amount of time that the low priority task takes to release the resource. Okay, so that is the solution that we have, which the OS implements, which is priority inheritance. Alright, so the moment the high priority task is blocked because of a resource that is held by low priority task, the low priority task priority is elevated to match that of the high priority task. And since now they are both at the same level, you no longer have any medium priority task trying to preempt you. Okay, you still wait. Of course, you still have to wait for this low priority task to run until the resource is released. But once it runs and releases, the high priority task will immediately be able to continue. Okay, and once the resource is released, you will also make the low priority task go back to the original level. Okay, it's only a temporary inheritance. So temporarily you inherit the high priorities level, but once the resource is released, you'll go back. Okay, so that is the solution that is actually implemented by the OS itself. Okay, so this is only applicable, okay, priority inheritance is only applicable in the context of using the mutex. Okay, so if you remember, I said that mutex and semaphore may look similar, but there's one key difference, correct? And this is the key difference. Okay, so if I use mutex as a mechanism to lock and release a shared resource, then when this priority inversion happens, the inheritance will kick in. Okay, but this is not applicable to semaphore. Okay, so the semaphore again is to manage sharing of resources, but a critical section of the code, then you use mutex. Okay, so if I use mutex, then I have this because it's automatically implemented in the OS. Alright, so that is why you must use mutex in the case of sharing any protecting shared resources or a critical section of the code. Alright, and then the priority inheritance will be able to help you if you are in the inversion issue. Okay, now besides priority inheritance, okay, so RTX implements priority inheritance. There are also other OS that may implement another variation of this called priority ceiling. Okay, so in priority ceiling, it is the same idea. Only thing is, the raising of the priority is done the moment the shared resource is acquired. Okay, that means when does this happen? So for priority inheritance, okay, it happens at the time when the high priority task is blocked. Priority ceiling is here. That means the moment the low priority task acquires a shared resource, I will temporarily raise my priority high. So it's sort of trying to preemptively prevent a priority inversion issue. Okay, in the priority inheritance, you wait until the inversion happens because you don't know whether it will happen, correct? It is not guaranteed that just because there's a shared resource there will be a priority inversion. Okay, so it may happen, it may not happen. Okay, so in the priority inheritance, it does not preemptively do it, it just waits and see if the inversion happens. If the inversion happens, then I do this priority raising. Okay, in priority ceiling, the protocol is to preemptively raise the priority the moment a shared resource is acquired by the low priority task. Okay, so the concept is the same, only is when I raise the priority. In inheritance, you wait for the block to happen. Okay, in the ceiling, you do it the moment the resource is acquired. Okay, so that is the only difference, but the concept is the same. Alright, so again, this is the important thing. Alright, and again, this is an issue, but again, the OS is able to take care of it for us. Okay, so preemptive scheduling is, again, like we saw, every task has a different priority and it will run until it's preempted. Okay, by the OS. In round robin, okay, we are using the idea where tasks of the same priority all will run for a fixed period or time slicing, okay, which allows them to share the CPU equally. Alright, in cooperative multitasking, every task has the same priority and each task will run until it reaches its end of its round robin time schedule. Alright, for RTX, again the default setting is this, round robin preemptive. Okay, or we call it prioritized round robin. Okay, as we have seen in the lab, all tasks that are equal priority will share the CPU, but if there is a task of higher priority, then that will take over. Okay, that will take over the CPU. Okay, again, please be mindful again that RTX is this is the behavior. In future, another OS that you use may have a slightly different behavior, okay, as the default scheduling context. Alright, so don't assume that this is how every OS will be. Okay, if in future you use free RTOS or use ThreadX or some other OS, then the way it behaves may be slightly different. Okay, so it's always good to read up on how the OS that you're going to deal with actually works. Okay, so that sort of wraps up this lecture. Okay, so before we go on to the next set of slides, just a quick recap on the midterm. Alright, so as I said in the announcement, okay, it's on this Saturday. Okay, it is 12 to 12:45. Alright, 12 to 12:45, LT 15 and 19. Alright, I will release the split later, who goes to where. Okay, duration is 45 minutes. Okay, 12 questions. Alright, open book. Okay, so any hard copy material you can bring. The appendix that I uploaded to Canvas will be printed out, okay, together with the test. So you don't need to print that out again, it's already together with the test paper. Okay, anything else that you want, you can print and you can bring along. Alright, okay, so as you saw for the practice paper as well, the code analysis is based on the style of coding that I demonstrate. Okay, and you see in the lab. So it's the same type of style of coding. Okay, chapter 1 to 10. Okay, the chapter on the analog interfacing is not included. I said that before already. Okay, that is not included. But other than that, chapter 1 to 10. So it's MCQ. So bring along 2B pencil and eraser. There will always be somebody who forgets this, I know. Okay, so if you are a kind-hearted soul, please bring extra. Then we can pass around. Okay, there is no negative marking, but 1 mark will be deducted for every unanswered question. Okay, why do I implement this? This is the same for finals as well. This to save me the hassle of going through all your paper again to see whether you shade or never shade. Okay, so make sure that you decide and you shade something. Okay, you decide and you shade something, so you don't lose mark unnecessarily. So there is no negative marking. So if you do not know what to choose, you just pray and then you see where your pencil lands. Okay, and then you choose the option. Okay, so I will send this as an announcement again, just as a reminder, but just make sure that you follow the timing and the venue once I release. Okay, so let's go on to the next chapter on this messaging and synchronization. Okay, so in this chapter we will we will learn a few more important techniques on how we can synchronize the multiple tasks that you have. Okay, so in the last lecture and in the lab also, you saw some idea of synchronization where you say that one task is waiting for semaphore and then another task release. Okay, then this task can continue. Okay, that is one possible way. Okay, but now we're going to see a lot of much more efficient ways of doing it. Alright, okay, so before that, do you want to be a TA? Alright, so usually towards the end of the semester, okay, so just to be clear, you need to do this process every semester. So even if you're a TA now, every semester you need to go through the same process, okay, which is you need to look out for the email by the SOC office where they ask you to register to be a TA. Okay, so you need to go to the link, you need to register, and you need to indicate the module, whether it's this module or other module, the same thing. You need to indicate which module you're interested in. Okay, and then the UG office has a vetting process. Okay, so they will go through the vetting process, and after the vetting process, then they will release or they'll update the website with all your names. Okay, so it's not guaranteed that whichever module you want you will get. Okay, but if you put it there, then there's a high chance that we will contact you. Alright, so if you don't see your name there, we cannot select you. Okay, so if you're interested, you need to make sure you follow the timing. Look out for the email and go register for whichever module you want. Alright, so next semester onwards, 2271 is transitioning to so-called blended learning. So what does that mean? Okay, so it means that all the lectures are supposed to be pre-recorded. Okay, all the lectures will be pre-recorded, and then the session is more of consultation and review, and then you go to the lab after that. Okay, so that is the new direction for 2271. Okay, starting from next semester. So we will not have tutorials separately anymore. Tutorials will be part of the discussion in class as a whole. Okay, and then we will have labs. Okay, so we'll have a few more lab sessions, maybe 3 or 4 lab sessions or lab classes depending on the size. Okay, so I think the class size will still be quite big, maybe about 100 plus, since we are allowing some flexibility. Alright, so I think we will need quite a few TAs. Okay, so just look out for the email and register. Okay, inter-task communication. Alright, so how can tasks talk to each other? How can they communicate with each other? Alright, so we're going to look at flags, events. Alright, so we already looked at mutex and semaphore before. Alright, and they provide synchronization. Flags and events are also options to provide synchronization. The last one over here provides synchronization with data communication at the same time. Okay, so we look at them one by one to understand. Okay, so flags. So what are thread flags? Thread flags are not created, they are already part of your thread. The moment you say OS thread new, you are actually creating thread flags that is part of the control block, the thread control block. Okay, and how do I use these thread flags? Okay, you need to reference the thread flags using the thread ID. So what is the thread ID? When you call OS thread new, you actually get back a return value. Okay, until now we never captured the return value, but actually that return value is what we call the thread ID. Okay, so you need to now create a new global variable, okay, under this data type OS thread IDT, and you can use this ID to reference the thread and the thread flags. Okay, so that is how you do it. So whenever you call OS thread new, the return value is a thread ID, which you now capture. Okay, now once I capture it, I can use it. Now how can I use it? Okay, so there's two functions, OS thread flag set and OS thread flags wait. Okay, so when I call these two functions, I must provide when I call thread flag set, I must say whose thread am I setting it for, and what are the flags that I want to set. Okay, and a thread that is waiting for it, okay, we'll call OS thread flags wait based on which are the flags that I want. Okay, and then I also have the options. Okay, options is in wait any, wait all, or and flag no clear. Okay, now let's look at this example. Okay, and understand how this thing works. Okay, so this is the code that you have there. Alright, now if we look at this code, okay, what happens? Okay, so there's two threads here, LED on and LED off. That means, firstly, when I call this LED on function, what happened? Alright, so assume that initially my LED is off. Okay, my LED is off. So I call LED on function, correct? Okay, so when I say LED on function, so let's say I go high. So this is the on. Okay, then I say flag set TID LED off. So TID LED off is what? It is the thread ID that I get back when I created this LED off thread. Okay, that means when I call OS thread new, okay, in my main function, okay, and I did the LED off, okay, it gave me a return, and that return was the TID LED off, the thread ID for this LED off task. Okay, and what am I doing here? I'm saying that for this particular thread, TID LED off, I'm going to set bit 0 flag. Okay, I'm going to set bit 0 flag. Okay, and after that I do a delay of 2000 or 2 seconds. Okay, so basically for LED on, after this I wait for 2 seconds. Okay, now when LED off thread runs, when LED thread off runs, the first thing I do is I say wait for the bit 0 flag to be set, correct? I say wait for the bit 0 flag to be set. Okay, now in this situation, the bit 0 flag has already been set, correct? The LED on already set the flag for me. Okay, if nobody set the flag means I will go to a block state. Okay, if nobody set the flag means I will have to go to a block state. But since LED on already set the flag for me, I can proceed. I don't need to go to a block state, I can proceed. Okay, so when I proceed, what do? I say delay for 500. Okay, so now I delay for 500. Okay, so I delay for 500 milliseconds, and then I say LED off. So I off. Okay, I off. Now after I off, what do? My LED on is still in the block state for 2 seconds, correct? So I won't go back there. So I look back here, correct? When I look back here, what happened? First thing I do is I say wait for the flag to be set, correct? But now nobody set the flag, correct? Because the last time that the flag set, I already cleared the flag. Okay, the moment I continue means I already cleared the flag. Alright, so since I already cleared the flag, I'm in a block state. Okay, so right now, this entire duration, I'm going to be in a block state. Because now nobody has set the flag. So if nobody set the flag, I will be in a block state until somebody set the flag. Alright, so eventually task 2 cannot run, correct? LED off cannot run anymore. Okay, LED off cannot run, it will be indefinitely blocked until somebody set the flag. Now who is going to set the flag? Only LED on, correct? And LED on is still in the delay. So when the 2 second is up, then I look back, correct? So LED off is now blocked already. It's waiting until somebody set the flag. Okay, and when the 2 second delay is up for LED on, I will come out of the delay, I will look back, I will say on again. Correct? When I on again, then I set this flag, correct? Okay, so when I set the flag, what happened? This will go to ready state, correct? Okay, the moment somebody has set the flag that I want, that I'm waiting for, the LED off will be able to come out of the block state and transition to the ready state. Alright, so at this point of time, the LED off is now able to transition out of the block state to the ready state. Alright, and then at the same time, I start another 2 second delay here. Correct? I start another 2 second delay here. Alright, and since LED off has now come out of the ready state, alright, I can now transition to the run, which is to delay for 500. Okay, and then do the off, and then again the whole cycle repeat. Okay, so that is the idea of using thread flag. Okay, so of course now you think, why is it so troublesome? Why must I have 2 tasks to just control one line on and off, on and off? So of course this is just an example. Now let's look at the second example, and then you get a better idea why this is very useful. Okay, this is your next slides. Alright, so in this example, okay, we have 3 threads, thread 1, thread 2, thread 3. Okay, now let's assume, okay, so now you have T1, T2 and T3. Okay, let me put T3 here and T2 here. Alright, now let's assume that thread 3 runs first. Okay, when thread 3 runs, okay, at some point of time, what will it do? It will say wait for flag bit 0 and bit 1 to be set, correct? Okay, so here I want the value to be 0, 0, 1, 1, correct? That means bit 0 and bit 1. Okay, both the flag must be set, then I continue. Okay, so at this point of time, when I reach this thread flag's wait, if both bits are not set, then I cannot continue. So I will go to a block state. Correct? So this is when I call the thread flag wait. Okay, for 0x3. Alright, so if both the bits are not set, I will become blocked. Okay, and at some point of time, task 1 may run. Okay, and what does task 1 do? It sets TID3, which is thread 3, bit 0. Correct? Okay, and at some point of time, task 2 will run, and when task 2 runs, okay, it will set what? TID3, bit 1. Alright? So when both of these events happen, alright, then it allows me to continue. Okay, so now you can see that this is actually quite useful, correct? That means I can say one task is going to wait for some other task to finish certain things. Okay, so task 1 finish something first, task 2 finish something first. When both of you finish your thing, then I continue my stuff. Okay, and how do I synchronize this? They all set some bits in the flag. So when all the bits are set, then I know all the requirements, all the resources that I want is set in place, then I continue with what I want to do. Okay, so this allows you a very nice way to synchronize, okay, the behavior and flow of the task. Right? So task 1 has to fulfill some objective, task 2 has to fulfill some objective, then when both of them are done, then I'll continue. That means I know that all the prerequisite is done. Yeah, correct. Okay, so why do this, correct? Okay, so basically your idea is you want to fulfill something. If let's say you know that task 1 and task 2 is going to run without any issue, okay, then you say sequentially I run and then I do task 1, task 2, task 3, correct? But in a real situation, you may not guarantee that task 1 can do everything and complete before task 2. Correct? So it could be a situation that task 1, okay, is doing something and it sends a signal, but at the same time, you do not want task 1 to only do this, it can also do other things. So if you see down here, the task 1 is not only doing this, correct? When task 1 signal to task 3, I'm not stopping. I'm still continuing what I'm doing. So this allows task 1, task 2, task 3 to eventually run concurrently, correct? Because task 1 and task 2 are not blocked when task 3 is running, correct? So all they're doing is saying task 1, I can do something. Task 2, I can do something. But at some point of time, I will signal task 3 to continue running. Okay, if you do sequentially means when task 1 finish, then task 2 do. Then task 2 finish, then task 3 do, correct? But in this way, we allow all 3 tasks to run concurrently. Correct? They run concurrently, but at the same time, they will signal each other when to continue some activity. Alright? So the only thing here is task 3 can do something before that. Okay, but at that point of time, it has to wait. Okay, but task 1 and task 2 are not dependent on task 3. When I send the flag, when I send this flag here, and when I send this flag here, I do not block myself in any way. I just set the flag and I continue what I want to do. Okay, so effectively task 1, task 2, task 3 are still running concurrently. Okay, so that is the difference between doing it this way compared to sequential. So you can do sequential if you say that task 1 do already means no need to do anymore, correct? Then task 2 do, then task 3 do. Okay, if it is your intention is to do sequentially like that, then you do it that way, correct? But if your intention is these 3 tasks must run concurrently, then this is one option. Okay, so this is one of the mechanism, the thread flag. Okay, so this is the slide that we just went through. So this is one way in which you can say that the different tasks talk to each other, okay, and run concurrently while making sure that one of the tasks wait for something else to happen and so on. Okay, so this is one option you can consider. Similar to that is another thing called event. Okay, the same idea. Thread flags and event flags are the same thing, same concept. Only difference is they are not tied. They are not tied to any particular task. Okay, just now we said that thread flag is when I create the thread, when I call OS thread new, I get the return, correct? And that is the thread ID, and I use the thread ID to set the flag. Okay, now in event flag, okay, the same thing, only thing is it is not tied to a thread, which means I need to separately create it myself. Okay, how do I create it myself? I must call OS event flags new, okay, and then create the event flag. And then subsequently the event flag set and wait is the same behavior. Okay, only thing is instead of specifying a thread ID, I use the event ID. Okay, but the behavior is the same. Okay, so this same, if you look at this code, it is exactly the same as before. Only thing is I specify the event I'm waiting for here, the event ID. Alright, so I need to first create event flags new. Alright, so this is now a generic event flag setting which I can use, okay, across multiple tasks. It's not tied to a particular task. Okay, in the previous case with thread, when I say set means it is only going to TID tree. Okay, when I call wait, I don't need to specify which thread ID because it's only the own thread ID. Okay, whenever I wait, I'm waiting on myself. Okay, for somebody else to send to me. Okay, but if I use event, I need to specify who am I waiting for, which event flag am I waiting for, because it is now a generic event flag. Okay, but the behavior is the same, the concept is the same. Alright, so this one I won't go through, it's exactly the same as before, only thing is instead of flag we have event. Okay, so now come to the last part, okay, which is a message queue. Alright, so what is message queue? Message queue is a slightly advanced way of synchronizing because it provides you both synchronization and ability to pass data between the two tasks at the same time. Currently, how you pass data between one task to another task? You declare 2000 global variables, correct? Okay, and then you share everything with everybody. Alright, so global variables, like I always say, is very easy, but it's also very dangerous. Alright, so you need to manage it very well. Okay, a more efficient or better way to share data without exposing your data to everybody is message queue. Okay, where I explicitly send a message from one person to another person, or one task to another task. Alright? And how do I do that? I create a message queue, okay, telling how big is the message queue and what is the size of each data packet that I'm going to send across. And then I can put a message called OS message queue put and get a message. Alright? So let me show you go through the code here first, and then I'll show the demo after that. Okay? So in the demo, okay, and in the lab, what you're going to do is, I've created a very simple data structure. Okay? Only 2 bytes. One is what you call a command packet, and the other is a data packet. Okay? Just 2 bytes, very simple. And then I create 3 different message queue: red message, green message, and blue message. Okay, and the 3 message queue is to send messages to each individual task: red, green, and blue. Alright, now in the message in the main, what I'm going to do is I create the 3 message queues over here, okay, and I put message count as 1. That means at any point of time I send 1 message. You can put 5, you can put 10, up to you. Alright, depend on how many messages you want in your buffer. Okay, but in my case I only put 1 because the moment I send, I will not send again until the message has been received. Alright, now how do I define the red and the green? Again, it's just an example. Okay, I put a command value, I put a data value. Alright, so let me switch back here. Okay, so the main so in the main I create the 3 message queue over here. Okay, later I'll show you the demo. Alright, and what does this do? It creates a message queue for anybody who wants to send a message to each of these ID, red message, green message, or blue message. Okay, and I use these 3 message queue for the 3 different LED. Okay, so similarly you can say, okay, maybe I create a message queue for motor, message queue for LED, and so on. Okay, but it's the same idea. Okay, you can create a message queue for different tasks that you want to manage. Okay, then over here I create a control thread. So beside the 3 thread, I create another thread called a control thread. Okay, so what does this control thread do? Okay, it populates my data packet. That means it puts the command value and put the data value. Okay, so the command is 1, okay, because it is LED control, and the data value keeps changing. So initially I put as 1, then I put as 2, then I put as 3, then I put as 4. Alright, and each time I put a message out to different message queues. So the very first time I only put a message out to red. Okay, the second time I put a message out to green. Third one I put a message out to blue, and then finally I put all 3 together. Okay, so you can send as many messages as you want to whoever you want. Okay, so there's no restriction. So you can send as many messages as you want to all the different queues. Alright, so this is the control thread. The control thread is responsible to send out the messages. Now let's look at the other side. Okay, what happens for each of the threads? So the code is the same, so I'm just showing you for one of the LED blue. Alright, so the first thing that happens is the thread is, first thing that it does is it calls message queue get. Alright, so let's look at this. So TR, okay, T blue and T green. Okay, the 3 tasks. So each of these tasks, when they run, the first thing that they do is they say queue get. Okay, so I'm trying to get some message from the queue, correct? So if nobody send me anything, what happened? I will block. Correct, so by default the design is to block until somebody asks me to do something. Okay, so if nobody asks me to do anything, that means I have not received any message, I will block myself indefinitely. Okay, until somebody asks me to do something. So okay, so all the 3 tasks will go to a block state when I first boot up or first run. Correct, because I'm waiting for somebody to send me a message. Okay, so the moment I receive a message on my message queue, I can unblock. Okay, I can unblock. Then once I unblock, then I go and process whatever data that I receive in this my RX data. Okay, and once I finish with whatever I need to do, okay, then I look back again. I look back one more time and wait for the next message to come in. Alright, so it allows you to have a framework where different tasks, okay, will do something when the main control thread tells you to do something. Okay, so in this example, my control thread is the one that decides who wakes up, correct? Okay, so the very first time, the red message will be sent out. So the red thread will unblock and process. Then the green, and then the blue. But in the final case, I send messages to all three at the same time, which means all three will unblock at the same time and run. Okay, so the running part, okay, this is just again a code to decide how frequently I blink. Okay, so if my data is 1, I blink 1 second interval. If it's 2, then it's half a second or quarter of a second and so on. Okay, so this is just an example to show that when I change my data, the behavior of the LED blinking will change. Okay, but the idea is the same. The idea is that all three messages, okay, all the three message queues allow me a framework, okay, to decide how the LED will go in sequence. Okay, so let me show you here. Okay, so today we're not having a break. We'll just go with the demo and then we'll end early, and then any questions you have, we can discuss after that. Okay, so just give me a minute. Okay, so let's look at the code and understand what's happening. So as we said before, the control thread puts a message out on the red first, okay, followed by the green, followed by the blue, and then all three together. Okay, so if I run the code, okay, what you will observe is red, okay, at 1 second, then half second, then quarter second, and then finally it is white. Alright, so I think the first three is easy to understand. The last part, again, why is it white, is because I send all three messages at the same time, correct? Which means that all three will unblock and run concurrently. So you see it as a white light blinking. Okay, so again, should I use message queue, should I use event, should I use flag, it's all up to you. Okay, so you decide what mechanism you want to use to allow the different tasks to synchronize or talk to each other. Alright, so again, like I said, last week and this week is important so that you now have all the tools. Alright, I already uploaded all the lab manual, okay, up to this, okay, which means you can go and try on your own, okay, and understand how event work, message queue work, and so on, okay, and then you, as a group, you all decide, okay, what is the best option to move forward. Okay, alright. So once you decide, then the rest is just putting in all the lower level blocks that you have designed. Okay, motor driver, LED control, audio control, everything. Okay, now everything will come together very nicely. Can? Okay, so that is basically it in terms of the thing that is really important to complete your project. Okay, so right now you have everything already to complete the project. It's just a matter of you all deciding and working on it. Alright, so for today that's all we have. Okay, we're going to end early. Okay, the tutorials for this week is spread across the two tutorial worksheet. Okay, so the scheduling We will move it a bit later. Alright, so we will just discuss the semaphore and mutex first for this week. Alright, later in the tutorial. Okay, so that's all we have for today. If you have anything that you want to ask me, any questions, you can come down and ask me. Okay, we can discuss or any ideas that you have. Alright, if not, thank you, and I will see you all next week. Okay? Okay, anything that you want to ask, please feel free to ask.